Good morning, children. So, as we all know, we have started with Science 1, lesson number 11, Reflection of Light. And in our previous video or previous lecture, we have studied about the properties of images formed by concave mirror. So today we will learn the properties of the image formed by the next type of mirror. Which kind of mirror is this, children? Yes, it is a convex mirror. So what is a convex mirror? A mirror whose reflecting surface is curved outwards is called a convex mirror. Now the question now is, how does an image formed by a convex mirror looks like? So let's find it out. So what we'll do, we will draw a table on the right just like we did for concave mirror. Here is a convex mirror. Suppose an object is kept at the finite distance away from it. Look carefully at this image formed. Can you tell me the property of the image formed by just looking at it? Okay, first of all, we conclude that the image is smaller in size compared to the object. This is very clear that the image is diminished. Okay, now the light rays seem to come from the point behind the mirror, but obviously we know that no image is formed there. So the image is also an upright image. Remember that every virtual image is an upright image. Now children, what if I move the object towards the mirror? If I move the object towards the mirror, the size of the image keeps on increasing. But the size of the image with respect to the object is always smaller. Now what will happen if I move the object away from the mirror? As I move the object away from the mirror, the relative size of the image keeps on reducing. Also, at finite distance away from the mirror, image formed is always virtual image. Children, do you know what is coming next? Don't you? Yes. What if object is infinitely far away? Well, in this case of a concave mirror, when the object was infinitely far away, the image was formed at a single point. It was a real, point size and highly diminished image. Point size means that the whole image of the object is formed at the single point. Here too, the same thing happens. Image formed is indeed point-sized, but here the image is the virtual image. So, when the object is placed at infinity, the image formed is virtual and erect. point-sized and highly diminished. Note this, that even the object is placed at infinity, the image is not at infinity. It is at a finite distance behind the mirror, even though the object is infinitely far away. In fact, this is the maximum distance at which image can be formed. Image in the convex mirror cannot be formed behind this point. We will now represent the image formed by a convex mirror using a ray diagram. Let's draw a ray diagram for this case first. Okay? This is when the object is at infinity. Our object will be the usual. And what is it? An arrow. And suppose it is at infinity. Now children, if you remember, I told you that the rays of the light coming from the object at infinity are considered to be parallel to each other. And we know that the two rays are sufficient to draw a ray diagram. So we will take any two parallel rays striking the mirror. Now these will be reflected in such a way that the laws of reflection are obeyed. We notice that the rays are diverging after reflection. And when we extend these rays backwards, what will happen? They meet at a single point, which is the principal focus in this case. Now what does this imply? When we are looking at the image of an infinity far away object, it appears to be formed at this single point behind the mirror. Now if the parallel rays are traveling in this direction, the image is still formed at a single point which is different from the principal focus. We called this point as focus, as it does not lie on the principal axis. What now? Now let the object be at finite distance from the mirror and try to represent the image form, for this case using a ray diagram. So how do we proceed? We only need to take any 2 points on the object which is represented by this arrow. Find out the image of these two object point first by drawing at least 2 rays emerging from each point. Now after reflection, all these rays will follow the laws of reflection. When we extend these rays backwards, we get a image location. I repeat again, that is not a real location in space. It's only a location where the image appears to be formed. I want to pause here for a moment to tell you the reason exactly why I chose these 2 rays only. One parallel to the principal axis and other directly to the focal point. Yes. These are not the random two rays. I chose them on a purpose. Now let's see. Well, if you remember children, when we were talking about the ray diagrams for the image formed by a concave mirror, we saw the rays which are parallel to the mirror will always pass through the focal point after reflection, and the rays which pass through focal point will always pass parallel to the principal axis after reflection. There we had only used these rays to draw all of our ray diagrams. Isn't it, children? Now, but in convex mirrors, we know that the rays cannot pass through the focal point as it lies behind the mirror. But if I direct the incident ray towards the focal point, then after reflection it travels parallel to the principal axis. Yes, any ray which is directed towards the focal point, it will travel parallel to the principal axis after reflection. Also, if the incident ray is traveling parallel to the principal axis, then after reflection it will look as if it originated from the focal point. For instance, here all these reflected rays seem to be coming from this focal point. With this bit of knowledge, now let's jump back to where we were initially. Now I think you understood the reason of why I chose these two rays. Okay, so let's quickly join this image points to get the complete image of the object. If we measure the length of the object and the image, we will find that the object size is greater than the image. So we say that the image is diminished. Also, one more important thing that I must say is that the image's distance from the mirror is not the same as the object distance from the mirror. So if you remember when we were discussing plane mirror images, the virtual image distance and the object distance from the mirror were the same irrespective of where the object is placed, isn't it? Here, even though it's a virtual image, it does not follow that property. So, these two are the ray diagrams representing the image and its properties. Understood, children? Now the next one, let us study the mirror equation. Now children, here we want to derive mirror equation. So what is a mirror equation? Some of you might know what it is and some may be hearing it for the first time. Since it has the word mirror in it, let's first draw a mirror. Should we draw a concave mirror or a convex one? Well, the mirror equation works for both. But let's start with the concave mirror. You are already familiar with all the symbols. P is the pole, C is the center of curvature. It is the center of a sphere of which the reflecting surface is a part of. The midpoint of C and P is the principal focus F. And finally, the line which joins all of them is called the principal axis. Suppose that our object is kept behind C at a finite distance away from the mirror. We draw our usual ray diagram to get the image, which is of course a real image. So what is a mirror equation? Well, let me just write it down first. 1 upon F is equal to 1 upon U plus 1 upon V. What do these three letters symbolize? They are nothing but distances between points. To understand better, let's draw a tangent at point P like this. In this equation, U is the distance between the object and the mirror. So this distance will be U. Okay? It is the distance point between points A and P. Remember, the distance between two parallel lines will always be the same. So this distance is nothing but the distance between A and P. Okay? Now V is the distance between the image and the mirror. Let's name this point as G. So V is nothing but the distance between G and P, and F is the focal length, which is the distance between the principal focus and the pole. This distance is equal to F. Note that all the distances are measured from the pole of the mirror and not some other point on the mirror. So from the equation you can see that it gives us relation between the object's distance from the mirror, image's distance from the mirror, and the focal length. What if instead of this I had placed an object somewhere else? It wouldn't change our formula. The equation does not depend on the object's position from the mirror. It is the same for any position of the object. What if instead of a concave mirror we had convex mirror? Again, it wouldn't change our formula. Yes, this formula is true for all types of spherical mirrors. Let's have a look at the summary. We have learned the properties of images formed by convex mirror. At the position at finite distance, the position of the image between P and F and the size will be diminished, that is small, and the nature of image will be virtual and erect. And At infinite distance, the position between at the focus, the size of the image is highly diminished and point size, and the nature of the image is always virtual and erect. Got it, children? What else we have learned? We have learned the mirror formula. So what is it? 1 upon V plus 1 upon U is equal to 1 upon F. So with this, we have finished our today's session. Hope you all must have understood and your concepts are clear about it. So children, we will continue in our next video. Till then, take care. Thank you, children.